Hello everyone, let's analyze. So today we're going to talk about functions of convergent sequences. That is, how are the concepts of sequence limits and function limits connected? To get a better idea of the connection, let's take a look at a picture. So let's consider a scenario where the domain of a function is the entire real line except for x0. And let's suppose that the limit of this function at x0 is some number L. And let's consider what happens if we have a sequence converging to x0. And we evaluate our function at this sequence of numbers. Well, in order for us to evaluate our function as xn converges to x0, we would need that xn is never equal to x0 because x0 is not in the domain. F of x0 is not defined. But we can see that if we graph xn versus f of xn in the magenta, then the values f of xn converge to L. Another way of seeing is, if we look at the sequence of numbers in the y-axis in blue, f of xn, they get arbitrarily close to L. And that makes sense because if xn gets close to x0, and the limit of f at x0 is L, then f of xn has to approach L. So let's make this concept concrete in a theorem. We say f has a limit at x0 equal to L if and only if for every sequence in the domain that converges to x0 but is never equal to x0, then the limit of values f of xn converges to L. Now, why might this theorem be true? Well, we're going to give a very rigorous proof, but let's just sketch out some of the ideas here. Right? We know that f has a limit at x0 of L if, for any epsilon greater than 0, there's a delta, so that if x is within delta of x0 but not equal to x0, then f of x is within epsilon of L. And those values are illustrated by the delta epsilon box. So then we could probably work out a sketch, a partial sketch of the proof. To prove this theorem, we would have to prove both directions of my if and only if statement. But let's sketch out an idea of why at least the forward direction might be true. If xn converges to x0, then there's a big N, such that if little n is greater than or equal to big N, then xn is within delta of x0, but not equal to x0 because we're supposing that xn is never equal to x0. In other words, xn is always in the domain of f. And of course, if xn is within delta of x0, right, then by the definition of a function limit, f of xn has to be within epsilon of L. So now that we see an illustration of how we might connect the ideas of sequence convergence and function convergence, let's prove this theorem rigorously. So let x0 be an accumulation point of D, which is the domain of the function we're considering, which is a subset of the real line. Then the following statements are equivalent. The function f has a limit at x0, and if xn is a sequence of elements in the domain, none equal to x0, but convergent to x0, then the sequence of values f of xn converges. So let's prove the theorem. First, let's develop a strategy. Step 1. Show that if statement 1 is true, then statement 2 must be true. Step 2. Show that if statement 1 is false, then statement 2 must be false. Now, one way to prove an if and only if statement, or to prove that two statements are equivalent, is to show that statement 1 implies statement 2 and statement 2 implies statement 1. But our strategy is slightly different, yet logically equivalent. To show that if statement 1 is false, then statement 2 must be false, we can diagram these steps as statement 1 implies statement 2, and the negation of statement 1 implies the negation of statement 2. That second step is really to prove the contrapositive of the implication statement 2 implies statement 1. So, logically, our strategy is equivalent to saying statement 1 implies statement 2, statement 2 implies statement 1. Of course, another way of looking at this is the true or false status of statement 1 has to match the true or false status of statement 2. And if that's true, then we say the two statements are equivalent. Okay, so now that we have a strategy laid out, let's execute the strategy. Step 1, prove that statement 1 implies statement 2. And this is what we've already sketched out in our illustration. Suppose f has a limit at x naught, and let's call it L. Well, what does it mean for f to have a limit at x naught? Well, it has a particular meaning. We defined it in the last lecture. It means for any positive number, let's call it epsilon, then there's a real delta for which the following is true. If x is in the domain, and within delta of x naught, but not equal to x naught, then f of x is within epsilon of L. So all we've written down is the definition of what statement 1 being true means. Now suppose that xn converges to x naught and also satisfies that xn is in the domain but never equal to x naught. If xn converges to x naught, we know there exists a natural number n such that xn is however close I want to x naught, and I want delta. Right? So for that delta, there's a big N, and if little n is greater than that big N, then xn minus x naught is less than delta. It's greater than 0 because I've assumed xn never equals x naught. Now, from statement 1, because xn minus x naught is within delta, but less than 0, then for those same values of little n, specifically those values greater than or equal to a big N, f of xn minus L is less than epsilon. Now, if I look at the statements in red, when taken together, that's precisely the definition for what it means for the sequence f of xn to converge to L, which means we've proven that the sequence f of xn converges to L. On to step 2, but a quick note before we begin. Just to point out that in statement 1 and statement 2, there's no naming of the limit. And so to make sure we're on the same page, let us understand that this limit has to always be the same. In other words, if for every single sequence xn that converges to x naught, f of xn converges, then f of xn must converge to the same limit L. In other words, I can't have two different sequences in the domain converging to x naught, never equal to x naught, and have f of xn and f of this other sequence converge to different numbers. That can't be possible. And why, you ask? Well, let me tell you. Because if xn converges to x naught and yn is some other sequence converging to x naught, then suppose I build a new sequence, x1, y1, x2, y2. In other words, I take my two sequences and weave them together. Well, then clearly this new sequence must converge to x naught. Why clearly? Well, because it was a previous homework assignment which you've done and understood very well, I hope. So because that sequence converges to x naught, then f of x1, f of y1, f of x2, f of y2, etc. also converges. And because that is a weaving together of two sequences that converge to L, that also converges to L. Therefore, it must be that any sequence converging to x naught in the domain, but not equaling to x naught, f evaluated at that sequence must converge to the same limit L. Okay, now that we have that out of the way, let's continue. Suppose now that statement 1 is false. Again, our goal is to show statement 2 is false. What does it mean for statement 1 to be false? Well, it means the function has no limit at x naught, right? There's no number L for which the limit of f at x naught is equal to L. Well, what does it mean for a limit to not exist? Well, for a limit to exist, something has to be true about every single epsilon. So if it's not true about a single epsilon, then we have a false statement, right? So there exists an epsilon greater than 0, such that no matter how close x gets to x naught, no matter how close, in other words, for every single delta, there's an x in the domain within that delta of x naught, and yet f of x is not within epsilon of L. Of course, if f of x is not within epsilon of L, it means the distance between f of x and L is greater than or equal to epsilon. Now, let's make clear our goal, which is that statement 2 is false. Right? Our goal is to show statement 1 is false implies statement 2 is false. So the negation of statement 2 is that there's a sequence xn that converges to x naught, where xn is in the domain and xn never equals x naught. However, f of xn does not converge to L, no matter what L is. Now, since delta in statement 3 is arbitrary, and that's important, right? Because when we negated statement 1, we said no matter how close x gets to x naught, f of x doesn't get close enough to L. So no matter how close means, right, x can get arbitrarily close to x naught, and still f of x is not within epsilon of L. So because delta is arbitrary, I can plug in any positive number for delta. So let me plug in 1 over n for any natural number n. So if delta is 1 over n, there's, right, for any delta, there's a number in the domain, right? So for every n, there's some xn in the domain that is within 1 over n of x naught, because that's what I'm taking my delta to be. And f of xn is not within epsilon of L. In other words, the absolute value of f of xn minus L, or the distance between f of xn and L, is greater than or equal to epsilon. So again, I'm just taking statement 3 and replacing delta with 1 over n, and the corresponding x is called xn. Now, 1 over n can be made arbitrarily small because this is true for every n. So because this can be made arbitrarily small, and there's always an xn in the domain that satisfies this. Now, how do I know there's an xn in the domain satisfying this? Well, because x0 is an accumulation point of the domain, so there's always, right, there's always a member of the domain arbitrarily close to x0. And so since 1 over n can be made arbitrarily small, it's clear that the sequence xn converges to x0. However, for every n, right, for every single n, there is an epsilon for which the distance between f of xn minus L never gets within, and never gets within epsilon of L. Right, to be greater than or equal to is to be not less than. That means the sequence f of xn does not converge to L, no matter what L is, because notice L was arbitrary from the very beginning. And now we've shown that the falsity of statement 1 implies the falsity of statement 2. Is falsity a word? I don't know. But I know that the theorem is true. We've proven it. Now, let's use the theorem to prove or possibly disprove whether a function might have a limit. So let's consider the function sine of 1 over x defined for all real numbers except for 0. However, 0 is an accumulation point of the domain. Does the limit as x approaches 0 of f of x exist? Well, let's consider the sequence of numbers 2 divided by pi times n. If I look at that sequence, as n goes to infinity, it clearly converges to 0, right? As n gets large, 2 divided by pi times n gets arbitrarily small. Now, what does f evaluated at those values look like? Well, f of xn is sine of 1 over xn, and sine of 1 over xn is sine of n pi over 2. And so let's graph those values. Well, we see that those values just bounce around from 1, 0, negative 1, 0, 1, 0, negative 1, 0. They bounce up and down, because I have this repeating pattern, 1, 0, negative 1, 0, 1, 0, negative 1, f of xn never settles anywhere. It never gets arbitrarily close to any number and then stays there forever. So the sequence does not converge. And because the sequence does not converge, statement 2 from our theorem is not true. And if statement 2 from our theorem is not true, then the limit at 0 of my function f cannot exist. So this is a very nice way of using that theorem to prove non-convergence of a function. We could have proven it by showing that the negation of a limit is true, but this is a really nice and straightforward way of showing it. So now we understand how the convergence of sequences and the convergence of functions are linked. In fact, it means that we can take a lot of our understanding about sequence convergence and apply that understanding to function convergence. For example, we can use this to show results about the arithmetic of function limits using the arithmetic of sequence limits. In fact, that's coming next lecture. That's all for today.